So last class we stopped with the discussion on subthreshold leakage, right? So we finished with subthreshold leakage. We said that the NMOS transistor can behave almost like a BJT because now the drain and source are so close to each other that the channel is so thin, right, that it behaves like a base. And if you remember, for BJT action, the base has to be very, very thin, right, and therefore you do have some current flowing through between drain and source even when the gate voltage is below the threshold voltage of the transistor, right. And we said that the most important thing was that subthreshold leakage, also referred to as I off many times when you say off state current. Today we will see a couple of more leakage mechanisms, but by default if you say I off, it is the subthreshold leakage. Okay, this is some I naught e power VGS minus VT by n phi t, right, into what, 1 minus e power minus VDS by phi t into 1 plus lambda VDS, right. This was the equation for subthreshold leakage. The most important part is really this exponential dependence on VGS and VT, okay. And as I said, as a designer, if you look at the plot of log ID versus VGS, it will look something like this, okay. And if you keep reducing VGS further, it will keep coming down. At some point it will go up, and this point is basically because of the introduction of something called GIDL, gate induced drain leakage. I won't even go into what this leakage mechanism is, but the only thing I'd like to say is that you can't indefinitely reduce VGS on a negative value and expect that subthreshold leakage will keep coming down. So there is a point at which you can, up to which you can go. Beyond that, subthreshold leakage may come down, but other leakage mechanisms take over, right, which is basically called gate induced drain leakage. Okay, this is what a designer should be aware of. This is where we stopped last time. So now let's proceed with a few more important things. So basically you have substrate leakage. So before we go into substrate leakage, if you have a simple PN junction, right, what happens if you plot the this is P and this is N, and if I apply a voltage like this, okay, then the current through the PN junction is some I naught e power QV by NKT, right, similar to whatever we had for subthreshold leakage, right. I just say let's leave it at this, proportional to this, okay. I am not even going to worry about all of this. It is proportional to this, which means that there could be an exponential current with the forward biased voltage that you are applying. And of course, if you look at this I versus V curve, this will be like, you know, after some cut in voltage it happens, and this is sort of some, you could have some negative voltage and then you can have a huge reverse bias leakage, breakdown current that will occur, okay. So these points are important because even if you reverse bias your junction, you should remember not to reverse bias it too much, because beyond that you can have a breakdown current, right. So we are going to apply these concepts now to an NMOS transistor and see what happens, what what are the conditions under which we can operate the device safely. N plus oxide. This is a P substrate. Now we said that I can have a body contact here, I can have a gate contact here, source could be grounded, drain could be some VD, right? So I'll call it D. Okay. Now what happens to the threshold voltage of the transistor if VSB comes down? If VSB decreases, VSB comes down implies VTH will decrease, right? So if VSB is coming down, it means that VBS is going up, right? VBS is a positive value. So if you apply a positive value, then you can get some either electrons or some depletion that happens, and therefore threshold voltage will come down, right? This is the back gate effect that we have abstracted out. So this is okay, good. You could have a larger current in the transistor by doing this, okay? But what happens if VB is connected to some positive value? Remember that this source is now grounded, okay, and VD also could be grounded when it is not being used. I mean, typically it would either be ground or it could be VDD, right, in digital technique. So for now, let's assume this is also VD, also grounded. So now this is my depletion region. So what you see is both the source and drain junctions, they are going to form PN junctions with the substrate, right? So there is one PN junction here, another PN junction here, and by connecting the body to a positive voltage, you are forward biasing that junction. What does forward biasing the junction mean? It means there is an exponential increase in current as shown here in this curve, okay? And therefore, if you are slightly increasing it, maybe 10 millivolt, 20 millivolt, maybe even 100 millivolt, sort of okay, but be prepared for the extra leakage that is going to come about. Of course, you cannot take it to 200 millivolts, 300 millivolts. Then the leakage will be uncontrollable after that, right? So you don't want to actually forward bias any junction in the transistor, okay? Rather than you don't want to, I should say you should beware of forward biasing any junction in the transistor, okay? So that's the right thing to say. Beware of forward bias PN junctions. The reason I say this is using the body to adjust the threshold voltage is a valid technique, and later you might try to connect this body to VDD and expect that the threshold voltage will come down and therefore I can do something. Well, that's not possible because the substrate leakage will kill you in that case, right? You should be very careful about which junctions are getting forward biased and what the magnitude of current is. You can use simulations to figure out what those currents are, right? It's not possible to come up with a back of the envelope calculation because this is really a second order effect, okay? But you have to be very careful and watchful about this leakage mechanism as well, okay? So the next leakage mechanism that we'll discuss, right, or as a designer that you should know about, is gate leakage. Okay. So when I had my long channel device, I had my N here, right, N plus P. This was my metal. I had a rather thick gate oxide. Okay, this was my gate oxide, right? And it was reasonably thick enough until about 45 nanometer. What does that mean? It means from 180 nanometer, 130 nanometer, 90 nanometer, 65, the transistor started shrinking. Why did they shrink it? So that you gain power, you gain area, you gain delay, everything, right? By bringing the drain and close together, closer together, we would achieve greater speeds. With that, you also got lesser area. You also got lesser power, and of course, why lesser power? Because if I bring these two junctions close by, I have to reduce my supply voltage also. Otherwise, the junction will break down. In all this, you were actually able to gain significant amount. Really, there seemed to be nothing which stopped you from scaling. It was all win-win-win, going from 180 down to 65 actually, right? Somewhere at 130, the subthreshold leakage started coming in and became a reasonable concern. 90 nanometer, it became a real concern. But up to 45 nanometer, you could just scale this device and obtain a new device which would just look like this. Okay, n plus, okay, and this would be my oxide thickness. There was no problem. The problem is, if you continue to do this beyond 45 nanometer, 22 nanometer and so on, what happens is this gate oxide becomes so small, right, that quantum mechanical tunneling can occur across the gate oxide. So if I ask you what's the current that is flowing into this gate of an NMOS transistor, what was your answer earlier? Ig is 0, because that is actually going straight into an insulator. Unlike a BJT where the base current is very, very small, right? And that is what is going to result in a larger emitter current, collector current and so on. Here the gate current is is negligible, is 0 in fact, right? If you scale the device, then this current started going up. Ig became greater than 0. This is purely a quantum mechanical effect. It cannot be explained through classical effects, right? The wave function of the electron would sort of go into the oxide, and there is a finite probability that the electron will be found on the other side of the oxide as well. And this forms a significant amount of current if you just blindly keep scaling your device. So what people did was they needed to do something to prevent this, right? Because your NMOS transistor, the greatest advantage is this gate current is 0. It's an insulator, so you don't have current flowing there at all. Okay, you will see the advantage of this later on. But the moment you break this assumption, lot of things actually break down. So people had to do something to stop this. So what people did was, they wanted to increase the thickness, right? Now if you increase the thickness, then your capacitance goes up, which means that the gate control actually comes down, right? So they had to do something where the capacitance remained the same, but my thickness still went up, so that the quantum mechanical tunneling sort of came down. You wanted to move this to a similar device, right? Small device like this, but with a, I'm drawing it slightly exaggerated, with a larger gate oxide. Okay, what do you want to do? You want to do epsilon naught A by T ox, right, to remain the same after increasing the thickness. How do you achieve that? Yeah, so what is the other parameter you have? If you increase your oxide thickness and you also increase epsilon naught by the same factor, then the capacitance would still remain the same, right? And that's why people started introducing high K dielectrics. From 45 nanometer onwards, 45 nanometer node. What is high K dielectric? You're just instead of using silicon dioxide as your oxide, you introduce some new materials, okay, which gives you a higher permittivity, relative permittivity, and the material that was used is hafnium oxide. It turns out that you can't put any material there because it has to now gel with silicon very well. There has to be very little defects when you go from silicon to hafnium oxide and so on. So now the gate stack, right, has become very, very complex. It's not just hafnium in fact there are many more materials, so that you can smoothly go from silicon to this other material, okay. So this allowed you to get an epsilon R of about 12. Relative permittivity of hafnium oxide is about 12. So therefore I could increase my gate oxide thickness by a factor of 3 compared to silicon, which is 4, right? Epsilon R is 3.9 or 4. So by a factor of 3 I could increase the thickness of my gate oxide, wherein I have killed quantum mechanical tunneling now, because that purely depends only on the thickness, right? But my capacitance has still remained the same, okay. But doesn't mean that this is very, very small, because in 14 nanometer the oxide thickness typically is 1 nanometer. In 14 nanometer technology node, let me say, Tox is approximately 1 nanometer, okay. So again the scales is very important when we say thick, thin and all that. Even with hafnium oxide and all that, we were able to come to about 1 nanometer, okay. So they have continued scaling after introducing hafnium oxide in 45, they have continued scaling further and brought it down to 14 nanometer, where it is oxide thickness is about 1 nanometer, okay. So typically as a designer now you don't have to worry about gate leakage so much unless you are doing some non-volatile memories and stuff, wherein you introduce defects and stuff like that, when the gate leakage can go up. But you should be aware that this could be a potential problem and you can't take it for granted that the gate current is 0, okay. Any questions? Yeah. Without? No, exactly. So it turned out that even in 45 nanometer, you had to bring this, see, the tunneling is also a function of the voltages, right? How much barrier, you need energy to cross those barriers. So in 14 nanometer, you have also been able to bring down the supply voltage from 1.2 volts or something in 45 nanometer, you would have brought it down to 0.8 volt. So therefore, you can bring the thickness down a little further. So it's not just the dimensions that scale, it's also your supply voltage that has to scale. So therefore, it is still sort of okay. Okay? Yeah. Okay, so with that, we have covered almost all the short channel effects that you should be aware of. Wherever possible, we have accounted and incorporated those effects into our level 1 SPICE model, right? Of course, we have not incorporated gate leakage and those equations we don't know. We really don't care also. You can use the simulator to handle those special cases, okay?